So, you think you've got gravity completely figured out, right? Let me ask you something. Step on a scale for a moment. Look at that number staring back at you. That's your weight, isn't it? The Earth is pulling you downward. Simple stuff. Drop something from your hand and watch what happens. It falls down. Consider the moon, endlessly circling our planet. Think about how the planets trace the sun in their cosmic dance. We've learned that objects possessing mass naturally attract each other. Newton solved all this hundreds of years ago. This thing we call the force of gravity seems remarkably easy to understand. Elementary, even. Except there's something. It's wrong, not just slightly off, mind you. I'm talking about fundamentally, profoundly mistaken about what's actually happening here. Snorts. Here's the truth that will shake everything you thought you knew. Gravity isn't even a force. Not at all. And let me tell you, when you finally grasp what gravity truly represents, when this understanding really clicks in your mind, the entire universe transforms before your eyes. Everything looks different. Come with me, and I'll reveal this to you. Stand up right now, at this very moment. Pay attention to the sensation of your weight. Now tell me something. What exactly are you experiencing right now? You'd say gravity, wouldn't you? The Earth dragging you downward. But I want you to really think about the actual physical sensation you're feeling. The floor, pressing firmly against the soles of your feet, pushing upward. That's what your nervous system is detecting. The floor pushing you. This mysterious downward pull everyone keeps talking about. You've never actually felt it. Not once in your entire life. You only experience the push, always pushing upward, never pulling down toward the center. So where is this supposed pull hiding? And here's something even stranger to consider. The moon is plummeting toward Earth at this very instant. It's been falling for billions and billions of years, yet somehow it never actually gets closer to us. It just keeps spinning endlessly, constantly falling, perpetually failing to land. Now, what kind of attractive force behaves like that? A pull that keeps pulling forever and ever, but somehow never manages to pull anything inward. And this is what Newton told us, according to his theory, that pull happens instantaneously. Change Earth's position, and the moon perceives it immediately across 240,000 miles of absolute vacuum. Instantly. How does that work? What physical mechanism carries that message? What's the actual process? Newton himself couldn't provide an explanation. He gave it a name, action at a distance, and openly admitted he had no understanding of how it worked. But you know what? The mathematics were absolutely beautiful. The predictions came out perfect every time. So naturally, people stopped asking those uncomfortable questions that kept bothering them. But they really shouldn't have stopped. Let's travel back several centuries in time. Nobody had any idea how the planets actually moved through space. Copernicus came along and announced they orbit around the sun. All right, perfect. But here's the real question. How exactly? What paths are they actually following? Tycho Brahe built an observatory and devoted decades to recording planetary positions, night after night, relentless year after year, measuring angles with brass instruments down to fractions of a degree. Now, why such obsessive precision? Because you simply can't understand nature's workings by making wild guesses. You have to look carefully. It's falling toward Earth, but it's also moving sideways, fast enough to keep missing our planet. It falls around Earth instead of falling into it. Why does an apple fall from a tree? The Earth attracts it. Same force, same underlying law, just operating at different scales. Newton performed a beautiful calculation. He calculated precisely how much the moon falls each second, how much its path deviates from what would be a straight line. Then he calculated how much objects fall here on Earth's surface. The numbers matched perfectly when he considered the difference in distance. Absolutely revolutionary. The force that pulls an apple is identical to the force that keeps the moon in its orbit. Heaven and Earth, governed by the same snorts physics. With Newton's law in hand, everything suddenly made sense. Ocean tides occur because the moon exerts a pull on Earth's water. The Earth is round, but it bulges outward at the equator because our planet spins on its axis. Comets return on predictable schedules because they're following elliptical orbits. Strange observations finally found their explanations. Jupiter's moons sometimes appeared early in their predicted positions, sometimes late. It turned out that light takes time to travel through space. When Earth is positioned farther from Jupiter, light takes longer to get here. This discovery led to measuring the speed of light for the first time. Planets wobble slightly in their orbits because they gravitationally pull on each other, not just on the Sun. From wobbles detected in Uranus's orbit, astronomers predicted the existence of a new planet, Neptune, and then found it exactly where they predicted it would be. For 2 full centuries, Newton's law of gravity stood tall as one of the greatest achievements in all of science. It explained absolutely everything anyone could measure with their instruments. But there was one peculiar detail nobody could adequately explain. Drop a hammer and a feather in a vacuum chamber. They hit the ground at the same instant, exactly together. Now the hammer has considerably more mass. So, according to Newton's theory, gravity should pull it harder, much harder than the feather. But the hammer also possesses more inertia. It resists acceleration more strongly, much more strongly. These two effects cancel out perfectly. Not approximately, but perfectly. Every object falls at exactly the same rate, regardless of its mass. Now here's the question. Why? Newton's theory requires 2 completely different properties of mass. Gravitational mass determines how strongly objects attract each other across space. Inertial mass determines how difficult it is to accelerate something. And these 2 distinct properties are always perfectly proportional for every substance ever tested, down to absolutely incredible precision. But why should mass's attractive property and its resistance to acceleration property be perfectly equal to each other? Newton had no answer to offer, just this remarkable coincidence that made the mathematics work beautifully. Or was it really just a coincidence? Einstein asked a completely different question. What if it's not a coincidence at all? What if that perfect equality is telling us something fundamental about what gravity really is? Here's a thought experiment for you to consider. You're inside a closed room with no windows anywhere. You feel your normal weight pressing you firmly to the floor. Are you sitting on Earth's surface, or are you inside a rocket in deep space, accelerating upward at 9.8 meters per second squared? Can you notice the difference between these 2 scenarios? Drop something from your hand. It falls to the floor in both cases. Throw a ball horizontally across the room. Curved path in both cases. Stand on a scale. Same reading in both cases. There's no experiment whatsoever that can distinguish between them. This is what we call the equivalence principle. If you truly can't notice the difference between gravity and acceleration, maybe they're actually the same thing. Maybe what we call standing still in a gravitational field is actually a form of acceleration. Here's Einstein's revolution that changed everything. Objects in free fall have no force acting on them at all. The falling apple, the orbiting moon, satellites spinning around, Earth, astronauts floating inside their space capsules. They're all in their natural state of motion, inertial, following straight lines through something called space-time. But space-time near massive objects isn't flat like a sheet of paper. It's curved, bent, warped by the presence of mass. So the straight line these objects follow looks curved to us observing from outside. You standing on the ground right now, you're not in your natural state. The ground is pushing you upward, constantly deflecting you from the path you'd naturally follow through curved space-time. That's what you experience as weight, not gravity pulling downward. The ground pushing upward, deflecting you from your natural trajectory through curved space-time. Einstein made a concrete prediction we could actually test. If gravity is really curved space-time, then light should also be affected. Light has no mass whatsoever. In Newton's theory, gravity shouldn't affect light at all. But if gravity is actually the curvature of space itself, then light, following the straightest path through curved space, should bend as it travels. During a solar eclipse, astronomers carefully measured the positions of stars near the sun's edge. The stars appeared displaced from their true positions in the sky. Starlight had bent when passing near the sun, exactly as Einstein predicted it would. This phenomenon is called gravitational lensing. We observe it in astronomical observations all the time now. Massive objects bend light from more distant objects positioned behind them, creating beautifully distorted images. Direct evidence that space itself curves in the presence of mass. Astronauts in orbit look weightless, floating freely. Zero gravity up there, right? Completely wrong. The gravitational field at the altitude where satellites orbit, a couple hundred miles up, is almost as strong as here on Earth's surface. Around 90% as strong, in fact. So why do astronauts float like that? Because they're falling. The capsule is falling. Everything inside is constantly falling toward Earth. But they're also moving sideways, incredibly fast. Around 17,000 miles per hour. As they fall downward, Earth's curved surface falls away beneath them at the same rate. They keep missing the planet. They fall around Earth instead of falling into it. Everything falls together at exactly the same rate. So there's no sensation of falling at all. No weight pressing on anything. No sense of up or down. It feels exactly like floating in empty space, far from any mass. This is the equivalence principle in action. Free fall in a gravitational field feels identical to floating freely in empty space because they actually are the same thing. In free fall, no force acts on you at all. You're simply following the natural geometry of curved space-time. Think about Earth's surface for a moment. It's curved into a sphere. But standing on it, it seems perfectly flat to you. And here's something truly remarkable to consider. Why is Earth round in the first place? Because of gravity, certainly, but not in the way you probably think. It's not that some mysterious force is pulling everything toward the center, actively molding Earth into a spherical shape. It's that space-time around Earth's mass is curved equally in all directions around it. Every piece of rock, every drop of water is simply trying to follow the straightest path through that curved geometry. And when everything follows those natural curves from all directions equally, you get a sphere. The only geometric shape where every point on the surface is at the same distance from the center. Earth is round, because that's what happens when matter follows spacetime's curves. The spherical shape emerges naturally from the underlying geometry. An ant walking what it thinks is a perfectly straight line on that curved surface is actually following a curve. But from the ant's limited perspective, it's moving perfectly straight. That's exactly what's happening with everything near Earth. Except it's not just space that's curved here. It's space and time together, woven into a single fabric. Space-time. Massive objects create curves in space-time. Depressions, wells, distortions in the fabric. The sun creates a deep well in space-time. Earth creates a smaller one. Even you standing there create a tiny well. Too small to measure easily. But it's genuinely there. Objects moving near these wells naturally follow the curves in the geometry. Not because something pulls them, but because they're following the straightest possible paths through the curved geometry. The moon orbits Earth because it's following the natural geometry of curved space around our planet. That geometry makes what would be the straightest path become a circular orbit. An apple falls from a tree because it's following curved space-time near Earth's surface. In that curved geometry, moving straight forward in time, points directly toward Earth's center. When you throw a ball across a field, it follows a parabolic arc, not because gravity is pulling it downward, but because it's moving through curved space-time, and the straight line in that curved space looks like a curve to you from your position observing. You're standing right now as I speak. You feel weight pressing you down. In Newton's picture, gravity pulls you down, and the floor pushes you up. Two perfectly balanced forces. In Einstein's picture, only one force acts on you, the floor pushing upward. But if only one force is acting, you should be accelerating in that direction. And you are. You're constantly accelerating upward, every moment. The natural path through space-time points toward Earth's center. That's the freefall trajectory. But the floor is blocking your path. It pushes you upward, deflecting you from that natural path you'd follow. You're like someone standing inside an accelerating rocket ship. The floor pushes against you. You feel weight, not from any downward pulling force, but from being accelerated away from your natural path through space-time. The apple hanging on a tree is also being constantly pushed upward by the branch holding it. When the branch breaks, the push suddenly stops. The apple is finally free. Free to follow its natural path through curved space-time. It falls, but the apple isn't accelerating at all. The apple is finally free to move naturally, following the geometry. Snorts. You standing on the ground are being constantly accelerated upward by the floor pressing against your feet. Falling is actually the natural state. Standing still requires a force to maintain it. That's Einstein's revolution that turned physics upside down. Once you understand gravity as geometry instead of force, extreme phenomena suddenly make perfect sense. A star is essentially a massive ball of gas burning in space. Its enormous mass creates a deep well in spacetime. The natural paths in that severely curved space point inward toward the center. What prevents total collapse? The pressure from nuclear reactions in the core, pushing outward with tremendous force. A delicate balance. When the nuclear fuel finally runs out, the outward pressure disappears. The balance breaks completely. The star collapses inward on itself. If the star is massive enough to begin with, the collapse continues until matter is compressed to absolutely incredible density. Atomic nuclei fuse. Electrons are crushed out of existence. What emerges from this cosmic catastrophe is a neutron star. Nuclear matter compressed to the size of a city. A teaspoonful of this stuff would weigh approximately 1 billion tons on Earth. For even more massive stars, not even neutron pressure can stop the collapse. Space-time curves so sharply, so extremely, that all possible paths through that geometry lead inward toward the center. Even light itself cannot escape from inside. This is what we call a black hole. Near a black hole, space-time is so severely warped that light itself, following the straightest possible paths through this extreme geometry, spirals inward and never returns. We can't see black holes directly with our telescopes, but we observe their effects around them. Matter falling toward a black hole accelerates dramatically, heats to millions of degrees, and radiates enormous amounts of energy before disappearing forever through the event horizon. All this from a simple idea. Mass curves space-time. Objects follow those curves. From this single principle, everything follows naturally. Planetary orbits, ocean tides, Mercury's perihelion precession. A small effect that Newton's theory couldn't adequately explain, but Einstein's theory predicts perfectly. Gravitational lensing, black holes, gravitational waves rippling through space when massive objects collide somewhere in the universe. The same principle that explains how the moon orbits also explains the largest structures we observe in the cosmos. Galaxies, galaxy clusters, the universal structure, elegant and unified. The pattern in the small piece reveals the design of reality's entire fabric. Newton's equations work beautifully for practical purposes in our everyday lives. We use them to launch satellites, calculate orbits, predict eclipses with precision. They're considerably simpler than Einstein's equations and accurate enough for most applications we encounter. But Einstein revealed what gravity really is at its core. Not a mysterious force pulling objects together through empty space. The curvature of space and time themselves woven together. Mass tells space how to curve. Curved space tells objects how to move through it. When you step on that scale, you're not measuring a downward pull acting on you. You're measuring how hard the scale must push upward to prevent you from following your natural path through curved space-time. When you see something fall through the air, you're seeing an object finally free to follow the geometry that mass has woven into the fabric of reality itself. When you look at the moon in the night sky, you're seeing an object following the straightest possible path through curved space around Earth. A path that looks like a circle to us because space itself is curved there. The geometry of space brings objects together naturally. That's what we call gravity, not a force pulling things around. Geometry guiding motion. And that's much more beautiful than any mysterious pull could ever be.